All right, I'm going to go over the regression classwork. And while you're watching this, there are a lot of concepts that are really important, especially for tomorrow's quiz. It kind of brings a lot of the contextual stuff about regression together here. We have to do a lot of interpretations. There's some new terms that I'm going to introduce as we do this, so please pay close attention to this video and learn from it. Okay, so the situation is we're looking at a response variable of the percentage of bicycle riders who wear helmets, and the explanatory variable is the percent of people receiving free and reduced lunch, sort of a measure of the socioeconomic status of these 12 neighborhoods. We can see by looking at this scatter plot that there appears to be a negative relationship between the two variables. We have summary information, the means and the standard deviations of the two variables, the 12 neighborhoods. But we also see that we actually have the regression analysis right here, which allows us to get the regression equation without doing any computation. So I don't need to use this information right here in order to get the regression equation. I can simply read it straight off this computer output. And we talked about the other day, get rid of all this stuff, that the two numbers that we want are this one and this one. This number here is the y-intercept, and that makes sense because it is the constant in the regression equation, and this number right here is the slope, and that makes sense because it is the coefficient on the explanatory variable, which is the percentage of people receiving free and reduced lunch. So the regression equation is, and I'm going to write it in context, it's the predicted percent wearing helmets. Okay, I put a hat there. Is 47.49 minus 0.5386 times the percentage receiving free and reduced lunch. Okay, so that's the regression equation. Make sure you know how to read computer output. Really important thing to be able to do. All right, interpret the slope and y-intercept of the equation in context. The slope is negative 0.5386. Let me write this interpretation. Okay, so here's my interpretation. For every 10% increase in the percentage receiving free and reduced lunch, we predict a 5.4% decrease in the percentage of bike riders wearing helmets. So you can see that here I've specifically interpreted this number. Okay, I'm not just being general about the negative association of the relationship, but specifically what does this slope of negative 0.54 tell us? And you can see I used 10% increase instead of 1% increase. You could have done 1%. You could do whatever you want, as long as you're reflecting this slope. Okay, so we see we have a negative association, and I don't know the reason for that. We don't know if it's a causal relationship, but you know, maybe neighborhoods that have more money, they can afford the bike helmets. Maybe they're more into safety. Who knows? We're not trying to say there's a causal relationship. We're just saying that there's a correlation. Okay, so the y-intercept is 47.49. So let me stop this and write an interpretation of that, and then we'll look at that. All right, so we know from algebra that a y-intercept is the value of the model, or the output when the x value is 0. So an interpretation here of the y-intercept is in a neighborhood with 0%, no one receiving free and reduced lunch, we predict that 47% of bike riders will be wearing helmets. Again, we're saying it's a prediction, and this is when the x value is 0. What's our predicted y value? Okay. Next question is, what is the correlation coefficient interpreted in context? Remember that the correlation coefficient is r. We're given r squared. Okay? Now, r squared is a percentage. R is not a percentage. R is between -1 and 1. So if we're going to take the square root of this, we need to take the square root of the decimal equivalent of that percentage. And so if we do that, we get 0.849. Now, this is not correct yet. we need to pay attention to the fact that there's a negative association. And we can see that with the slope here. So actually R is the opposite of the square root of 0.721. And so we get negative 0.849. That's the correlation coefficient. And let me write a quick interpretation of that. Okay, and remembering that the correlation coefficient measures the strength and the relationship of the linear correlation, of the strength and the direction of the linear correlation between the variables. We can write an interpretation that says there's a strong negative correlation between neighborhood socioeconomic status and the percentage of bike riders wearing helmets. Make sure you don't interpret this as a percentage. Okay, that's really important. It's simply a number between -1 and 1. Correlation, the coefficient of determination, that's called R squared. R squared is given to us. It is 0.721. That can be interpreted as a percentage. And let me write an interpretation of that. All right, so I'm going to say that 72.1% of the variability, and highlighting some keywords, in the number of bike riders, that's the response variable, number of bike riders wearing helmets, is explained by our model. Okay, so at some point you'll just have to kind of memorize this kind of canned interpretation. It's the percentage of variability in the response variable that is accounted for or explained by our model. But if you remember how that came about, it was we measured the total variability around the y, we measured the amount of variability that our model could explain, or actually couldn't explain. That was sort of our error, and what was left over was the variability that the model could explain. Okay, so and we can interpret R squared as a percentage. All right, moving on to the back, we're going to use our model to make some predictions. We're going to predict the percentage of bike riders with 30% of students receiving free lunch. This is simply plug and chug into our model. And we pay attention to, if we look at the data, the percentages are as percentages, not as decimals, so that's going to be a 30 there. And we get here, they're about 31.332% is our prediction. If we plug into that equation, 95%, we get 47.49 minus 0.5386 times 95, and we get something that's a little bit perplexing. It's a negative percentage. So if we think about that, that's impossible. So how confident are we in our prediction here? Well, no way. It's impossible to get a negative percentage of people wearing helmets. I don't know what that means. I don't know if that means that we have to take helmets off people in other neighborhoods or whatever, but this is impossible. Okay, so here's some new terms. This 95%, if you look at the data, there's really no neighborhood that has a percentage receiving free and reduced lunch above 80. So 95% is outside of this range. This type of prediction is called an extrapolation. And we're not really confident about extrapolating in a linear model. First of all, it gives us an impossible answer. And second of all, we know models are wrong. And further, they're probably more wrong the further away from the data that we have. Okay, so this is an extrapolation. The question before, this is called an interpolation. Okay, two words that you should know and write down: interpolation and extrapolation. Interpolation is when we predict inside the range of the data. We're much more confident in predictions in here than we are out here. Okay, so two words you should know. All right, find the residual for the Toyon neighborhood. I'll pause this for a second. All right, so a residual is an actual minus a predicted. So I looked up Toyon and I found the actual y value was 32.34. I need to find the predicted y value. I plugged in 19 into our regression equation. I got this is the predicted. I subtracted those numbers and I found that the residual is negative 4.92, which means we overpredicted by 4.92 percentage points. Okay? Next question says, interpret this residual plot. This residual plot is a plot of all the residuals versus the percentage receiving free and reduced lunch. Okay? And if you'll recall, and we haven't talked about this too much, we're looking to see if there's a pattern to these errors. If there were a pattern to these errors, then we would try to fix our model to account for that pattern, which would mean that the model we created is inappropriate. And we created a linear model, so that would mean that a linear model is inappropriate for the data. Well, we can see here that there's really not too much apparent structure. So no apparent structure, which basically means that our linear model that we created is appropriate. Now, it's not perfect, but we know models are not perfect. Okay. All right. Number 9. Suppose we wanted to switch the explanatory and response variables. What would the new regression equation be? Would the slope be the reciprocal of the slope of the original equation? Well, at first thought, if you think about, y hat equals a plus bx, and you switch the x and y and you solve the new y, the new slope that you get for switching those variables will be the reciprocal. However, that is not the case in regression. When we're switching the explanatory and response variables, we're not simply solving this equation for the other variable. Okay? We're actually recomputing, I'll call it the new slope, and that's going to be r times s sub y over s sub x. Okay? So if I go back to the front, I find that r is negative 0.849. The y variable now is the percent receiving free and reduced lunch. I go back to the original table of data up here. We're actually going to use this now. And we can see that 26.72 is the standard deviation of that variable. And the standard deviation of the other variable is 16.95. And that slope is negative 1.34. Okay? This is not the reciprocal of the original slope. The only thing that flipped was this, okay? But we're still multiplying by this correlation. So it's really important to understand that if we switch the explanatory and response variables, first of all, it's not surprising that the slope will change, but the slope will not be a reciprocal of the original slope because in regression, we have to multiply by that correlation coefficient. Okay, so we get this new slope, and we're going to plug back in to find the y-intercept, so let me do that. All right, so all I did here was I took and plugged into this equation. I have an actual y and an actual x, and the slope I just computed. I solved for the y-intercept, and I got this was the new equation. Okay. All right, finally, part B. What will the new correlation coefficient and coefficient determination be? The slope will change, okay, although it won't be the reciprocal of the original slope, but the correlation coefficient will not change. These values will not change. If r doesn't change, clearly r squared doesn't change. And so it's important to note that if you switch the explanatory and response, the correlation is not affected. Okay? All right. So a lot of stuff on this handout. Tomorrow's quiz will have a lot of these concepts in it. It's a good review and also a couple new things. So make sure that you really pay attention to this or watch it again. Thank you.